and welcome to the day 3 of the second week of this course. In the last class, we learnt about how to classify the symmetry operations of any given molecule in terms of the point groups. We learnt about the point group symmetries also. We also verified the whether the symmetry operations, the exhaustive list of symmetry operations can act as the elements of a group or not, and we saw that yes, it does, and those are called symmetry point groups. And we actually systematically figured out how to actually systematically find out the point group for any given molecular structure. So today we will look at some particular molecules and we will try to find out their point groups. Okay, so that will give you a very nice practice because this is very much needed, because in the following weeks, when we would like to utilize the the principle of group theory in order to find out several properties. Okay. Say for example, when we would try to find out about the selection rules for any spectroscopic transition, or we would like to find out what are the atomic orbitals that can combine and form a symmetry adapted linear combination. So there you would really need to find out the point group and the symmetry operations within that point group real fast. Okay, because that will be the basis of very other things that we will do. So let's start with a molecule which is on your screen, is water and ammonia. So this molecule water, which is a bent structure, we have been dealing with this for quite some time, and we know exactly what are the symmetry elements and what are the symmetry operations that are possible for this this V-shaped molecular structure of water. So we know what are the symmetry elements. So you can see you have C2, which is along this axis. You have two sigma planes, which are sigma V and sigma V, denoted as sigma V and sigma V prime. One contains all the atoms, while the other one bisects the HOH angle. And as usual, you have the identity operation. So the total symmetry operations are 4: E, sigma V prime, and C2. Now, having all that in my hand, let's start finding out with what is the point group. So what was our rule? First question that we should ask, if you remember step 1 in the flow chart that we discussed in the previous class. So the first question is the molecule linear? Here for water, the answer is absolutely no, because it's a bent molecule. Okay, so that doesn't belong to either of C infinity V or D infinity H. Next, the question is, are there multiple higher order of rotational axis? Answer is again no. I have only one rotational axis, and that is C2. Okay, so I do not have n number of Cn where n is greater than 2. So that doesn't belong to. So this molecule doesn't belong to either of tetrahedral or octahedral or icosahedral point groups, not among those point groups. The next question is it is the molecule has only identity operation as its sole operation? The answer is obviously no, because I have 4 operations: E, sigma V prime, and C2. So okay, so it doesn't belong to C1 point group. Does it have only sigma other than E? No, so it is not CS point group. Does it have only inverse center of inversion other than E? No, it doesn't even have inversion symmetry. So it doesn't belong to CI. The next question that we ask is there an even order improper axis of symmetry? That is, does it have something like S4, S6, S8? The answer is no. I do not have any improper axis of symmetry. So let's not worry about that. directly let us go to step 4, okay? Step 4 and 5. So, we ask, do we have a proper axis of symmetry? Yes, we do. What is that? We have a C2. Okay. Now, next question that I ask, are there n number of C2s perpendicular to this principal axis? So, if I rephrase the question, are there 2 C2s perpendicular to the C2 that we found here? Answer is no. So, according to our methodology, the molecule must belong to C type of point group. Clear? All right. Next question is, does this molecule have sigma H? Answer is no, I do not have any sigma H. Sigma H means it should be perpendicular to the principal axis of symmetry. So, I do not have any plane which is perpendicular to C2. So, this does not belong to C2H. Next question is, okay, are there n number of sigma V's? Here you go, you have it. You have 2 sigma V's, 1 sigma V, 1 sigma V prime. So, your point group is CNV, n is 2 here, so C2V. So, the molecule water has a point group which is C2V. Okay. All right. Let us move to another molecule, ammonia. So, first we have to know what is the structure of ammonia. Ammonia is a pyramidal structure, right. So, this N and 3 hydrogens are there. So, 3 NH bonds, they are at equal distance, all 3 hydrogens are at equal distance from each other. So, if I add the tips of this finger which stands for this NH bonds, then that will form an equilateral triangle. Very fine. So, then in that case, if I ignore the lone pair of electrons, which is not very much material because they are very highly symmetric, what are the symmetry operations? So, I can clearly see there is one C3 here. So, there is one C3, and along each NH bond we have a sigma plane. You can see sigma V. Here is one of the sigma V, another sigma V. You can differentiate them by sigma V prime, sigma V double prime, or sigma V1, sigma V2, whatever way you want. But the matter of fact is, I have 3 sigma V's, I have a C3. So, the number of operations that the C3 can generate is 2 other than identity. So, you have C3 square. So, are there any other operations? No, you can verify that. So, I have the total list of symmetry operations which are like which we have E, we have C3, we have C3 square, we have sigma V's. So, I will write 3 sigma V's. Okay. So, this is 3 sigma V's. Very nice. Now, let us ask those questions stepwise. Molecule is not linear, molecule does not have an S which is even, molecule has many other symmetry operations other than only I or only S, only sigma. So, it does not belong to C1, Cs or Ci. And next question is, are there any principal axis of symmetry which is not a natural consequence of Sn, where n is even? I do not have any S, so let us not bother about that. So, essentially what I have is a principal axis of symmetry as C3. Okay. So, and that is only one principal axis of symmetry. I do not have any multiple principal axis of symmetry. So, that my molecule does not belong to any special category of groups. So, now I ask the question whether there are 3 sigma 3 C2s perpendicular to this C3. Answer is no. So, my molecule belongs to C type of point group. Now, next question I will ask is, are there sigma H? I cannot see any sigma H, it is a bent molecule. So, there is no sigma H possible. Then are there sigma V? I can see, yeah, there are 3 sigma V's. Okay. So, definitely the molecule belongs to C3V point groups. All right. So, we are learning how to find out the point groups with the particular example. Now, I talked about this linear molecule, right, when we were classifying the different molecular structures in terms of their symmetries and assigning the point groups. So there we asked a question, is the molecule linear, and if the answer is yes, then it belongs to two different type of symmetry point groups. One is D infinity H and another is C infinity V. Okay. Here are the examples on your screen of this D infinity H and C infinity V. So in the first case here, it's just a ball and stick model kind of, you can think, or also you can think this particular structures it is very similar to structure of carbon dioxide, right. So both the balls are of equal size, and this is another ball. So this carbon and two oxygens. So here you have infinite number of rotational axes, so it belongs to a special group. Now one more feature is that I have a plane which is here and which is perpendicular to this principal axis, and this is a sigma plane perpendicular to this C axis, where the C axis is particularly C infinity. We have discussed this in one of our previous classes, that there are infinite number of rotations possible along this axis. So this molecule belongs to D infinity H. Whereas if I take a molecule like this, okay, so you can think about certain examples, like if I say like HC, maybe HCl, okay, the easiest example, hydrochloric acid. So if I take an HCl molecule, here obviously you have something like 3 atomic molecule, but the same example can be given with HCl also. But here let's look at this. So I have C infinity axis here, but I do not have a sigma plane. So I do not have any sigma plane here. So next question will be, there are infinite number of sigma plane here. Yes. So you can imagine many sigma plane in this orientation or any other infinite number of orientation. So the point groups are sigma V, C infinity V. Okay. So now let's move to another example of an octahedral molecule, which is like this, MX4Y2. So when I if anyone asks you what is the structure of this molecule MX4Y2, any student of inorganic chemistry will say it's an octahedral molecule. True. Now what is the symmetry? Okay, we will see that, and for comparison we will also see what will happen for a molecule which has something like MX6. If someone asks me, I will say, oh well, both the molecules will be octahedral. Now in terms of symmetry, this MX6 and MX4Y2, they may behave completely differently, and so we can sense that their some properties will be different. So MX4Y2, I have here 4 x's, and the y's are here. So what are the symmetry elements that I have? What is the principal axis of symmetry? I have a C4 here, right? So that's my principal axis of symmetry, and let's now try to find out the point groups without not going through every steps, because as you do more and more, you will be very familiar looking at the molecular structure. You will be able to figure it out that what are the symmetry operations that are possible, and what will be the point group. So let's do it in that way. Okay, so that will help you also in finding out this point groups a bit faster. Initially, obviously, you go through this each and every steps very meticulously, but as time progresses, you will see you can do it like the way I am going to do it now. So I have a principal axis of symmetry. I know there is no there is no SN axis, like there is no S8. So this C4 is a not a natural consequence of S8. Okay, so C4 is there, very fine. Now is there any is there any perpendicular plane to this C4? Knowing that okay, there are not more than one C4 here. Okay, I am talking about the element. There is not more than one C4. So this is the only one principal axis of symmetry, C4, and I can see there is a plane, okay, containing all this x's and the m. This mx4, that plane constitute a sigma h. So this is my sigma h. Okay, so that's all I want. I mean, I have got my point group. So this you have a principal axis of symmetry C4, and then you have a plane perpendicular to it, which is sigma h. So very easily I can tell the molecular point group is D4H. See how it is, how easy it is. Okay, so you don't have to go through all those things, but you should keep that in mind. Then only you can do it rather faster. Now, as I was saying that I will also check what happens for MX6 molecules, and here we go. So in MX6, see, all this are X, okay, and the central metal is here. So this is my metal, and these are all X. So all the MX bonds are equidistant. In the previous case, it was not like that. So here, what I have a C4 axis. Okay, so if I imagine an axis through this, so this is one C4. Now all the bonds are exactly the same. They are disposed at exactly the same angle with each other, meaning that this angle and this angle, they are equal. So every angle here is 90 degree. The distance, this distance is equal to this distance, right? So I can have another C4 along this axis, so I can have a C4 rotation. So like this. So similarly, I can have another C4 along this axis, so I can have a C4 here, right? So I have more than two higher axis of symmetry. Okay, so this definitely belongs to a special group. I don't have to go to any further. Okay, and then you ask certain questions that we did there. Okay, does it have I? Yes. Then you ask again, does it have a C5? Then answer is here there is no C5. Then what is the choice we have? The choice is it's an OH symmetry. So this is a this particular molecule will have an octahedral symmetry. Symmetry is octahedral obviously, and the point group also will be OH or octahedral, you can say. So this is my point group. So you can see these two are different, okay, and their properties also will be different. All right. Now you can, just like the molecule, you can find the point group to which any given structure belongs to. So on your screen you can see there are certain geometric shapes. So the first one is that of a tetrahedron, right? So in that special quality of a tetrahedron is that all the vertices, they occupy the opposite corners of a cube. So here this is my tetrahedron, right? So tetrahedral structure, you can find out what are the symmetry operations. So for a tetrahedron you have more than one C3s, like exactly the way we found it for CH4, right? So you have multiple axis of higher order symmetry, higher order rotational symmetry. So this molecule will belong to special group, and if you follow the steps you will find out that this molecule belongs to, this particular structure belongs to TD point group. Similarly here this will belong to OH point group. We just now did this exercise using MX6 molecule, and this particular structure will be having icosahedral point group. Okay, if you follow up in this particular case, I mean you cannot see all the faces, so that may pose a little bit of difficulty toward you. If you could rotate this molecule Okay, so I mean, like if you could rotate and you could see from different perspective, you would see that, well, it has multiple axes of symmetry for sure, and then it will have I, and then you will have this C5 axis. So it will belong to icosahedron point group, IH point group. Okay, so let's go through some bit more number of examples. Okay, and many of the examples that I have taken from the books that I have suggested you as a reading textbook. This book is by Professor Cotton. So now we will look at the structure of molecule allene. Okay, we have looked at water and ammonia. Now we will look at find out the point group of allene. So what is allene? So you have a structure like, very easily I can write like this. Okay. Right? If I write in the proper stereochemistry. Okay, so from here you can find out several symmetry elements for this particular molecule. Now it will be a much better idea to view it in a different way. Okay, that will be pretty helpful. You can use this molecular, this kind of perspective, but another perspective will be much helpful for you. So that I am going to put up on the screen now. So you can see the one that I was talking about. So you see the one that is above the plane of the board, another is the below the plane of the board, and these two are on the plane of the board. Okay, this two CH bonds. So this structure can be presented in terms of like a parallelepiped, and this hydrogens will occupy the the opposite corners of this parallelepiped, pretty much same way as that any tetrahedral molecule, if you want to show in a cube, it will be pretty much same like that, right? So now you can think, you can see the symmetry operations much better, much with much easiness. So you can easily figure out that along this particular axis, if you rotate, so this H3 here, it will go to H1, and this H4 will go to H2, and vice versa. So you will get an indistinguishable structure. So that is 1C2. You get 1C2 here. So this will come here, and this guy will go here, right? So that will act as a C2, and there is one more C2 along this axis, which is shown here. So here things are slightly, you have to be a bit careful, because one clause was there: are there multiple axes of higher order of rotational axis? Here have to you have to keep in mind that this higher order of rotational axis, that means n is greater than 2. Now here I have altogether 3 C2 axes. So 2 C2s are perpendicular to 1 C2, and this is not, n is not greater than 2, n is equals to 2. So this doesn't belong to that particular category. So it will not go to a special category. So rather we choose one particular C2 as the principal axis of symmetry. So fine, I get one C2 and then 2 perpendicular C2s to this. So this is quite sufficient to move to the next step and find out its point group. So I got already I got C2 as the principal axis, and then I got 2 perpendicular C2s, which are always written as C2 prime. Perpendicular C2, perpendicular with respect to the principal axis of symmetry, they are denoted as C2 prime. So, I have two C2 prime. So, by now I know that molecule belongs to a D type, and then I have to ask, okay, do I have a sigma H? In this particular case, I take any of the C2 as a prime principal axis. You will find out there is no perpendicular sigma plane. So, now I take this C2 as my principal axis of rotational symmetry, and I do not find any sigma H. So, I do not have sigma H. So, no sigma H. But then next question is, are there two sigma V's? Here in this case I should ask sigma D's, because I have already seen that this belongs to sigma D, this belongs to D type of point group. So, the next question is, are there two sigma D's? The answer is yes. Why? So, if you take this plane, okay, so the plane, so if you take this plane, this will cut this H1 C1 H2 bond into half, and also this C1 and C2. So, this will be a symmetry plane. Similarly, this plane will also do the same function. So, if you extend this plane throughout this body of the parallelepiped, you will find out that very clearly. So, we have two sigma D's, okay, and therefore, this molecule ultimately belongs to a point group which is D2T. I knew that, okay, this is D type and there are two sigma D's, so it is D2T point group. Now, one more thing you see here, that how this structure, the way you draw, it helps you in finding out the symmetry operations. So, in this particular structure, this is behaving exactly like a structure of methane. Here you can see that though there is no proper no proper C4, but if you assume that there is something like C4, suppose this does not exist actually, but I am telling that, okay, suppose you rotate the molecule by 90 degrees. So, as if you have a C4 and then you reflect it on a plane perpendicular to this C4. So, what will happen if you rotate by C4, this will go here and this will come here, and then when you reflect this on this plane which is perpendicular to this C4, this will be appearing here. I am sorry, then this is not there. So, now my new structure is here, right. So, this will now go here and then this one will go here, correct. Similarly, this part will also change accordingly, and ultimately you will get your original structure back. I mean, here in this case indistinguishable structure. So, essentially this axis will act as an S4 axis. So, it will be little difficult, I will not say impossible, it will be little difficult if you just draw like CS2, CS2 and try to find out S4. So, this particular way of drawing here, it really helps you in finding out this S4 axis. Okay. So, I will give you another few quick examples. So, for example, hydrogen peroxide. So, what is hydrogen peroxide? It can exist in two different forms. Okay. One is like this, cis, and then another is trans, and I am considering here both the structures to be planar. So, cis planar and trans planar. So, this one is trans and this one is cis. Okay. So, what are the point groups of this? So, this one you can see easily, you have a C2 along this axis, and there is a molecular plane containing all all the atoms. So, there is one sigma, if I can just draw this molecular plane, fine. So, this I call it sigma V, and then another one which is bisecting this O O bond. So another is like if I draw, so this is another sigma plane which I call it sigma v prime, and this sigma v prime is perpendicular to the sigma v. So these are the all symmetry operations that I have. So I have C, C2, I have sigma v and sigma v prime. So if I just follow, I have C2, there is no S or no I, no special type of group. So this belongs to C type of point group because there is no particular perpendicular C2s with respect to this C2. So this belongs to C type, and there are no sigma H, but there are 2 sigma V's. So the molecule belongs to C2V point groups. So this structure. On the other hand, here what are the symmetry operations? I have one C2 along this, and this axis in the plane of this molecule. Okay, so this is one C2. Another C2 I can think of which is perpendicular to the plane of this molecule. So if I can write like a stereo structure. So this is at the bottom. This is one C2, and then what I have a plane containing all these molecules, right? There is one mistake. So this is this particular axis is definitely a C2. I sorry, this is not a C2. No C2 is here. Okay, so what I have a C2 here. I have a molecular plane which is also perpendicular to this C2. Then I have a sigma H essentially, and then I see here this hydrogen has an as a counterpart. If I just pass through this point and extend it, so it is here. Similarly, this O will find another counterpart if I go here. So every point on this molecule will find its counterpart if it passes through this central point. So I have an I. So what we all have? I have E, I have C2, I have sigma H, and I have I, and there are no other possibilities. So what is my point group? Definitely it belongs to C type. I can see that because it doesn't belong to any special type of group. And when I ask whether there are n number of perpendicular C2s, then the answer is no, and therefore this belongs to a C type. And then the next question is there any sigma H? The answer is yes, sigma H is there. So my point group is C2H. Okay. So with this we will stop today. In the following class we will try to look at a few more, and then we will look at some of the properties of this point groups, some of the characteristics of this point groups, and also we will try to look at does this symmetry classification help us in finding some physical properties of these molecules, like say polarity or a chirality for per se. So that's all for the class today, and I'll see you tomorrow. Thank you very much.